a few things to note from this, or just before y'all start your warm-up, you have a Canvas quiz that opens today. It opened at 8 o'clock this morning. You get 2 attempts, and after that second attempt, there's no eligibility to like your grade changing whatsoever. You have those 2 attempts to make sure that you are working through it diligently with those 2 attempts. It closes on the 21st, which is next Tuesday. So I would suggest not waiting until the very end to try and do it and scrambling. I would say try to get it done 1 attempt at some point this week, and then if you don't like that first attempt over the weekend, try a second attempt, or at least get it started. It is due on the 21st, opens today. It covers anything that we have covered this year, so any topic that's been covered is fair game on that quiz. Okay, so what y'all are doing first, if you have a sequence where the first term has a position of n, how would you notate the previous term? What about the next term? What this is saying, if we have a sequence or we have a number, any number in our sequence, if we're talking about the previous term, so the one before it, thinking about how we could take that phrase, the one before it, how could we write that mathematically? Our original term is in position n, so the previous term, the one before it, one before, how do we write one before mathematically? It would be a -1. So the previous term would be n minus 1. What about the next term? So the next term, the next one, the one in the future, so adding 1 on, would be n plus 1. Where this is going to come in, we're talking about arithmetic sequences again today. We're going to be using this notation that uses n minus 1 or n plus 1 or any of that. This is talking about the previous term. So we're going to go through something called the recursive and explicit rules today. So as we're moving through, it's different ways to write a sequence. So recursive is one way, explicit is the other. So we're going to take that time. There's different notations for each. It's still those sequences that we were talking about on Friday, though, where it's adding something to move through the sequence or subtracting. That's adding a negative. So it's adding something to move throughout the sequence. So if you look at your notes on the very top, we have this sequence. We're going to write this out in words. So as we're moving through, I hope you can see that it's adding 2. So our common difference is 2. And turning that sequence into a table. The first term is 2. The second term is 4. The third term is 6. The fourth term is 8. The fifth term is 10. So we're going to, in those line spaces, we're going to write the sequence out in words to describe a sequence. So anytime we're describing a sequence, you have to include, it says it up here, our starting value. That is important in a sequence because if you just say we're adding 2 each time, okay, then could my sequence be -1 and then I'm counting forward, so then I have 1 and then 3. Oh, that's not matching the numbers that we have in our sequence. So the first thing you always have to mention is our starting value. So it starts with 2. Then add 2 to the previous term. So that's saying that we're adding 2 to move on to the next. Things are important, starting with 2, and then we're adding 2 to the previous term. So we're going to take that same idea and do number 2. Looking at our sequence for number 2, our first term is 3, our second term is 6, our third term is 9, our fourth term is 12, our fifth term is 15, Hopefully you're seeing here that it's adding 3 each time, so our common difference is 3. And then turning that into words again. So again, the most important thing, or one of the most important things to include, or something you always have to include for these sequences, is our first term. Our first term in this one is 3. So it starts with 3. Then add 3 to the previous term. Starts with 3, adds 3 to the previous term. Okay. So what we're about to look at is the recursive rule. We just wrote this out in the recursive rule format. So the recursive rule is how we build a sequence. We use the recursive rule if you're ever just asked to make a table of sequence. The recursive rule, we're not plugging things in to solve anything. What we're doing with the recursive rule, the purpose of it is to help build that table, build the sequence itself. So it's not on here, but, well, there's an example of the recursive rule, but I'm going to write it out to the side. How we write the recursive rule is how we set it up in the words. We're always going to have to write the first term is whatever that first number is. Let me change that. So notice I have an A with that subscript of 1 because that's the first term. So we just have to always write out what the first term is. Then we have a comma, or you can put a semicolon, whatever. The rest of the term, so A sub n, we're taking this second portion that we said. We're adding 2 to the previous term. So we're adding our common difference to the previous term. How we write that mathematically, that's going back to the warm-up. How we just talked about previous term, we write n minus 1 as a little subscript to our A. So our previous term, and we add whatever our common difference was. This looks more complicated than what it is. Because when we're talking about what do you actually do with this problem, or what do you do with this equation, you fill in 2 parts. You fill in the first term and the common difference. That's it. We're not filling in anything else. We fill in those 2 parts with our important parts from the sequence. It says it right here. We require 2 parts, the first value, and then the pattern of the sequence, which is our common difference. Again, the purpose of this form is just to help you build the table. So if we look at this example right here, here's our sequence. It's already worked out for you. There's your sequence. The common difference is 2. So turning it into the recursive rule, this is it. The first term is 4, and then we're adding 2 each time. You have to include all of that other notation though, but you're not doing anything with it. It's just writing out the first term and then the common difference. Okay, there are some more examples down here if you need to see them. What we're going to do is go to the next page. So go ahead and flip it. So the purpose of the recursive rule and how it's helpful, if we look at these first 3 examples, or these first 3 problems at the top, it's helping you build the sequence. What this is saying is the first term is 7, so we have a sequence, the first term is 7, and then we are adding 4 to get to the next sequence, or get through the rest of it. So 11, and then 15, 19, 23, dot, dot, dot. Or if we look at the next one, our first term is 12. Then to get through the rest, that's what's in that second part. It's the previous term minus 3. So we're going to be subtracting 3 to move through the rest. So 9, 6, 3, 0, dot, dot, dot. to repeat that pattern. Okay, so what I want you to do is pause the video, and during that time that the video is paused, I want you to fill in the rest of the sequence for part 3, and then I want you to do this part, which is matching. You're matching the different sequences to the different parts over here. So pause the video, fill those out, press play when you're ready to check it. Okay, so checking your answers. For the sequence you fill in was -5, -3, -1, 1, 3. And then your matching goes D, B, C, E, A. Hopefully we went okay with that. Okay. So now for our next part, what we just went over, all of these here are examples of your recursive sequence, your recursive way to write the sequence. The recursive purpose, there's nothing to plug in terms of solving anything here. Your only purpose for the recursive is to help build a sequence, build a table. Now, if you have a problem that's saying, here's the sequence, find the 100th term, okay, the recursive rule, I don't want to make a table all the way to 100. So there's a second way to write a sequence, and that's called the explicit way, the explicit formula. So we're taking the explicit formula. The purpose of this one is to actually use it to solve equations. So this is the one that's helpful if we need to do anything other than build a table. Why do we have the first one then? Well, we just do. It's called the recursive rule. But the explicit one is the one that helps us if you're finding a table or a number in the future, or if you know some random number that's in the sequence to find out the position that it's located in. So if we turn to the next page, that's where we're going to find the explicit rule. Okay, so our explicit formula is right here. And I like to rewrite it a little bit. So this is saying we have our any term in our sequence, a sub n means any term in the sequence. It's our first term, because a sub 1 means our first term. And then plus this n minus 1 times your d common difference. I like to rewrite it where this common difference is in the front of the parentheses because we're going to be using it to distribute. So I like to rewrite it like that, just because we're going to be distributing when we solve it. So things to notice about this. The things that are still important are the exact same things that were important when we talked about the recursive rule. We have to have our first term, and we have to have our common difference. Those are still our critical bits of information when it comes to a sequence. So here's our sequence. If we look at the problem down below, so we're going to look down at this problem. Here's our sequence. 3, 5, 7, 9, 11. Using that explicit form, I'm going to do it over here. A sub 1 plus d, and then n minus 1. The explicit rule is the one that we actually plug into, we actually solve with. We plug in 2 spots. First term, common difference. So using our sequence, that's adding 2 each time. So our common difference is d, or common difference is 2. Our first term is 3. So first term, common difference. Those are our critical bits of information. To write your equation, it would then be 3 plus our common difference, which is 2, and then n minus 1. That is the full expanded version of our explicit formula. Now, when it comes to explicit formula, we can simplify that right side a little bit. This is actually an equation that we would use. So simplifying that, we could distribute 2 out to n minus 2, and then we can combine our like terms. So this would be 2n plus 1. Okay. Now I'm hoping maybe one person either kind of read or you're looking and you're thinking, oh, that kind of looks familiar. It should look familiar. This, once you simplify it, is your slope-intercept form. It's in that form of mx plus b. Knowing that, I'm going to give you a little bit of a hint. We don't necessarily have to use this explicit formula, that exact one, because it's not on your formula chart. Instead of doing that, if you know the tools how to write something in slope-intercept form, well, it simplifies to that, so I'm always going to be good with that, a simplified version of something. So we're going to go into these examples and try it in, we can try it both ways, but I'm going to show you something that you might like a little bit better instead of having to memorize this recursive rule formula. So here's our table, or here's our first example. It's saying number 1, and as we move through, it's adding 4, so our common difference is 4. Our recursive rule, let's just knock that one out. The recursive rule is the two-part, the one that we started class with, where we have to write our first term is whatever the first term is, which is 4. Put a comma, semicolon, whatever, and then to get the rest of the numbers in our sequence, it is the previous term, and then we just said our common difference is adding 4. Okay. Recursive rule, knocked it out. Knocked it out of the park, we're done. Okay, the explicit formula, if we wanted to go about the way of doing it with that exact rule itself, that would be our first term, which is 4, plus our common difference, which is 4 times n minus 1. And then we would go through and simplify it, so 4 plus 4, n minus 4. Combining like terms here, so that would just be 0. So 4n would be our final simplified version. Okay, that is option 1. I'm going to show you the alternative way to get there. Get this answer without that other work. To get that answer without the other work, we're going to envision our sequence at the table. So our sequence at the table, our first term is 4, our second term is 8, our third term is 12, fourth is 16, and then fifth is 20. So doing all of that like normal. What we need, if we want something in slope-intercept form, let's have a thought for a moment. Slope-intercept form, we just did that last week. We need the slope and the y-intercept. The slope, okay, well that's adding 4 as we go up 1. So our slope is 4. So when it comes to writing your equation, we get 4n, or 4x, same thing. Okay, we also need the y-intercept. Thinking about what a y-intercept is. A y-intercept is when x is 0. In my table, could I go backwards to get 0 for x? Okay, you're all thinking, yeah, duh, of course. That's just going backwards 1. Okay, well, let's go backwards with our common difference. Instead of adding 4, let's subtract 4, which is 0. So our slope-intercept form, 4n plus 0, whoa, doesn't that simplify this? Ta-da! So let's try that again. Actually, before we do that again, we're going to fill in the rest of this part for number 1. So how this is now helpful. Getting the 50th term, this is the equation, that simplified explicit rule is what we use to get the 50th term. That'd be plugging in a 50 for n. So 4 times 50, which is 200. Then we're also going to graph it. So graphing those word pairs, we have 1, 4, we've got 2, 8, 3, 12, kind of fits, kind of not. So just put it on there, and then we can be done. We're only graphing the sequence itself, so we don't need to graph the y-intercept. We don't need to connect the points, because connecting those points means that we're graphing all of those numbers in between. The sequence is 4, 8, 12, 16, those very specific numbers. So we're not including all of those things in between. Now let's go down to number 2. So, same idea. We're going to fill in like the common difference, the recursive rule. We can even do the table and graph. Then we'll do the explicit. So, moving along, our common difference is adding 3. In our table, our first term is 5, our second term is 8, third term is 11, fourth term is 14, fifth term is 17. I'm going to go ahead and graph it. We can't graph all of the points, so we're just going to graph what we can. 3, 11, okay, we can kind of do it right there. Okay, and now for our recursive rule. For the recursive rule, that's the long drawn out one, the one that we don't actually use to plug anything in. It helps to create and describe a table. Our first term is 5. And then to get the rest of our terms, it's the previous term that we had plus 3, which is our common difference. All right, now we're going to get into the explicit rule. For the explicit rule, the regular non-simplified version, it's our first term plus our common difference, and then times n minus 1. That is the non-simplified version. I need y'all to recognize that that's the explicit one, but what I really want is that you can also write the simplified version. To get to the simplified version, you can either simplify your explicit rule, or take our table, use slope-intercept form, because it is slope-intercept form. To get our slope, that's adding 3 as we add 1. So our slope would be 3, so that goes our variable. And then to get the y-intercept, we have to go backwards 1. So going backwards in our table, that means instead of adding 3, we can subtract 3, which would give us a 2. So plus 2. And we're done. You don't have to do that work of simplifying it. If you're comfortable, slope-intercept form, which you should be. We just did it last week. Okay, and now using this is the equation we use to find the 50th term. 3 times 50 minus 2. 3 times 50 is 150, so 150 minus 2 is 148. Okay, so now what I want y'all doing for the remaining part of class, there's a back. I want y'all to work on the entire back page, finish it up. If you finish before class is over, go on to Canvas, check yours, see if you did it correctly, see if you have all the right answers. And then once you have that done, you can work on your test review. Y'all got your test review today. It's due Wednesday. That is what your homework is to work on some of that test review. So you can work on that once you have checked your answers on that. Okay, I'll see y'all tomorrow.